You, me, the building in which I am, Paris, our planet, like practically the universe in its entirety, revolves around this pendulum, whose story begins where great men end. Indeed, it was in the Pantheon that Foucault installed for the first time in 1851 this strange pendulum. Even if the original version is now here at the Museum of Arts and Crafts, where the public can still come today to admire this invention, which shows and demonstrates that the world turns. And to pay tribute to the ingenious beauty of this experiment, we will often, in the manner of an oscillating pendulum, move from one place to another. At first glance, observing these back and forth movements, one might think that there is nothing particularly crazy, except for the size of the device itself. Except that where it starts to get weird is that once launched, this pendulum seems to very slowly deviate from the axis in which it was initially released. By observing this swinging movement for several minutes, we can see that the lines shift slightly, gradually, by a little more than 2 mineti per oscillation, until eventually, knocking down one by one, the small metal pins arranged on either side of the pendulum's initial oscillation plane. And we might be tempted to say that it's simply the movement of the latter, which, moving clockwise, deviates towards the pins, comes to meet them. But we will see that this interpretation is just an impression, an illusion. In reality, something stranger is happening here, because the plane of oscillation of a pendulum, which is only fixed by a point at its top, which is not like those of clocks constrained in an axis, once launched, does not pivot at all and always maintains the same direction, the same plane. An oscillation plane that remains invariably fixed, as can be shown here with a reduced pendulum model, whose oscillations do not deviate at all when its support is rotated underneath it. In other words, the drift over time of such a pendulum is only apparent, and its plane of oscillation remains fixed, no matter the direction in which it was initially launched. And where it becomes astonishing is that here you actually have the same thing, but on a much, much larger scale. A most ordinary device that shows us something extraordinary and allows us to answer a question almost as old as the world itself, namely, is it the Earth that rotates on its axis, or the stars that revolve around us? And the proof that it is indeed our planet that rotates on its axis is given there, without even needing to look up at the sky and observe the stars. Because if this pendulum does not deviate over time, and yet we see it deviate, then it means, as crazy as it may seem, that it is us who are revolving around it. Let's pause for a second on this dizzying idea. It's the Earth beneath our feet that, by turning, carries this building, which is placed on it like the table that is there and the pins that have been arranged on it. Pins moving a few millimeters with each oscillation come to meet the pendulum and end up crossing the plane of oscillation. I'm going to repeat it differently for you and also a lot for me. It's the pins, the table, the Pantheon in which we find ourselves, which all turn at the same time as the Earth around its axis, and therefore move in relation to the plane of oscillation of the pendulum, which remains fixed. And all of this can be shown using a single, simple pendulum of enormous size. Here, the one hanging from the dome of the Pantheon has a cable 67 meters long, supporting a lead and brass ball weighing 28 kilograms. At the Arts and Crafts, it's a 19 kilojoule sphere swinging at the end of a steel cable, 18 meters long. And in either case, if these Foucault pendulums are so monumental, it's primarily to allow them to operate long enough to see the Earth rotate below. Because invariably, friction, air resistance eventually overcome their swinging. And even the most imposing of them run out after a few hours. And there, perhaps you're wondering how long it would take the pendulum, the world below, to make a dial turn. Hold on, because the answer to this question is both fascinating and a bit disturbing. When we provide a bit of energy to the device to power it, maintaining its movement as we know how to do with electromagnets located under the table. One might expect that, by analogy with clocks, 24 hours would be necessary to complete a full rotation around the plane of oscillation. However, what makes it exceedingly bizarre although it already was, is that this is entirely untrue. The experiment, repeated hundreds of times, demonstrates that in Paris, an object takes just over 32 hours to complete a full rotation. This duration must seem completely counterintuitive to you. If you haven't understood anything so far, don't worry. It means you're completely sane. In fact, Foucault himself, when he noticed that the plane of the pendulum seemed, and it's always seemed, to take about 32 hours to return to its starting point, had trouble sleeping at night. Warning: the explanation, in terms of sensation, is like inverting your brain, extracting it through your eyes, and fashioning a hat from it. The pendulum's apparent rotation time varies with the latitude of the experiment's location. Imagine setting up this device at the geographic North Pole. Once started, the pendulum begins to oscillate in a fixed direction. And beneath it, the Earth rotates counterclockwise, without disturbing its axis. An outside observer, penguin or human, placed nearby, would therefore see the pendulum shift apparently gradually in the clockwise direction until it finds its initial axis after 24 hours. So far, so good. Except that we notice that the closer we get to the equator, the longer the pendulum takes to complete a full turn of the dial. Sorry, I meant to say, the more the objects that surround it and slowly revolve around it take a long time before giving the illusion that the plane of oscillation has made a full turn of the dial. And it takes to perform a complete rotation relative to the pendulum about 32 hours in Paris, 43 in Casablanca, 48 in Cairo, and so on, the duration increasing as we approach the equator. A region where, then perpendicular to the axis of rotation of our planet, the pendulum no longer deviates, apparently all the time necessary for the ground beneath it to go around it from the back to infinity. Listen carefully. It's the sound of one of my neurons just bursting. Beyond that, heading south from the equator, the pendulum starts to deviate again, apparently, and the time needed to make a full rotation gradually decreases until it reaches 24 hours at the geographical South Pole, where you would go around it in the company, this time, of a penguin. If you are bleeding grey matter from your nose, and rest assured, in fact, our brain is absolutely not equipped to represent rotational movements in space. And so, to put it politely, it's extremely difficult, without getting into mathematical equations, to visualize the movement of a pendulum that's tilted sideways, relative to the Earth's axis of rotation, and which itself spins at the same time as it swings. And the craziest part about all this is that this extremely simple experiment can also take you into mind-bogglingly complex considerations, and it takes you along with it into questions that start in this room and end at the far reaches of the cosmos. Because not only has it made history by allowing us to tangibly perceive the Earth's rotation, the Foucault Pendulum also offers you a mental journey through space, an adventure beyond the solar system to the boundaries of our universe. For this final journey, you must hold on to whatever you can find. In short, to any object revolving around this plane of oscillation, which remains fixed, does not change over time, regardless of the direction given to it. But what does it mean to be fixed? Fixed in relation to what? In nature, absolute motion does not exist. Hold on to anything. It is always relative, and one moves in relation to something else. Movement can only be described relative to a fixed reference point. I am currently stationary in relation to the ground, but not in relation to the pendulum around which I am slowly turning, carried in the direction of the Earth's rotation. And we cannot talk about my movement without defining a frame of reference. However, if the direction of the pendulum's oscillation never changes once it is launched, if its plane of oscillation is forever fixed, in relation to what is it? In other words, are there, up there, in the space of the stars, objects absolutely stationary in relation to the plane of the pendulum's oscillation? To try to answer this question that might dislocate your neurons, let's try to consider the movement of the latter, not in relation to the rotation of our planet, but by going a little further. Imagine that you place the pendulum at the North Pole and you start its swing towards the sun. The first few days, you would see absolutely nothing happen, the plane appearing to remain fixed in relation to the Sun. But over time, imperceptibly, our star would begin to shift, to drift, and after a few weeks, it would completely exit the plane. And if we oriented this plane of oscillation this time towards stars located a few light years away from us, hold on tight. This is also what you would observe, with the only difference being that the time required before seeing these slowly drift out of the plane would be much longer. But in the end, they too would end up leaving after several years of experience. Don't let go, hold on tight. If we were to aim for even further stars, if we were to point, say, in the direction of Andromeda, or even more distant galaxies, well, we would observe over several months, years, or millennia, these objects gradually moving away, and eventually they too would exit the plane. In fact, even if extremely distant stars give the illusion of being fixed in relation to the oscillation plane, since the time required to drift from it increases with the distance to the pendulum, all will inevitably end up leaving it. And the thing to remember is that the further away the objects we aim for, the longer they take to exit the plane. And it's only at the furthest we can observe, at the level of objects located at the edge of the observable universe, 13.8 billion light years away from us, that the drift seems to stop. You can stop holding yourself. The plane of oscillation of the pendulum finally seems to remain fixed in relation to the most distant objects that can be detected in the direction it points. And the conclusion of these observations is simply extraordinary. This means that the behavior of the Foucault pendulum, the direction it maintains once launched, its movement, owes nothing to our planet, our Sun, the billions of stars and nearby or distant galaxies. But it is directly dictated by the entire universe. You can let go of everything. The pendulum's axis of oscillation seems to have finally settled. It has now become immutable. In other words, it is only by considering the universe as a whole that we can define a frame of reference in relation to which the plane of oscillation remains perfectly fixed. But how to interpret this strange behavior? How does the pendulum appear to be intimately linked to everything else? Is its behavior determined in a global framework? Is what happens here, this movement, really influenced by the totality of structures populating the cosmic immensity? We are touching on the great unresolved questions of physics. The nature of this possible mysterious link existing between all the objects of the universe, if it exists, remains unknown. And to give the gaping holes dug by these oscillations inside my skull time to fill up, I'm going to stay here, contemplating this simple oscillating pendulum which, 170 years after its invention, still projects you into the infinitely large, allows you to see the Earth turning live, and perhaps also a bit the stunned spirit, the universe.